Hello.
Hello.
Hello. Hello.
Hello, Mr. and Mr. Ryan. Are you alright?
Good. Yeah.
Okay, so we talked about the graph the day before yesterday, yeah? The connectivity between the start and the finish, right? Okay, Eric, that's it. The graph, yeah? Bidirectional graph.
See it.
That's okay.
Oh, shaded.
The graphs. How can we represent a graph? That's it. How can we represent a graph? Alright?
Using
Graph. What do we represent the graph? What letter are we using to do the graph? Which graph? Graph start with Z, yeah? What does it contain?
It contains
What's this, Eric? What's this?
edges.
This is edges, and what's this?
No, vertex.
Vertex, yes. G we use it's a collection of vertex and edges. Okay, that's the graph. So we want to find out if there's a connection. If
there's a path that it can lead to the end.
we're done from 1 to 5. Is that no?
No.
1 to 3.
Yes.
We're done. Okay, and then we can use the buffer search, right? Yeah.
Because 1 to 5, there's no path.
Yeah, exactly. Okay. So buffer search, they are level by level. We use the queue, and we also use the notebook to remember the vertex we have visited, right? And then how do we represent the graph? We use the adjacent linked list. Actually, it's adjacent linked list, not adjacent linked list. Yeah. Linked list. What does that mean? Yeah, it's not adjacent matrix. Previously, I made a mistake because it's not adjacent matrix. It's adjacent linked list. Why is that? How do we represent this graph? The key. The key is the vertex, right? Remember?
Yeah.
So if it's 1, vertex 1, and then the value is the list of vertex it can connect to. So what's 1? What's here? 1 can connect to 2, a list of 2. 2 can connect to
1 and 3.
yeah, 1 and 3. 3 can connect to 2, a
And
list of
1.
no. It's just direct edges. 3 only can connect to, and then 4 connect to
5.
5, and then 5 connect to
4.
where the you see? So the keys are the vertex, and the values are the list of the vertex it can get directly connected to. Yeah. Okay. So that day we used the buffer search. Now today we're going to use the depth search. Okay. Yeah, it's quite similar. We still need to use the hash set. Yeah, a hash set to remember the nodes we have visited, so it doesn't form a cycle. Look, if I visit 2. If I come from 1 and visited 2, right? And should I visit 1 again? Do I need to visit 1 again? No, right? Because if I go back to 1, what happened? Then you will go to the 2 again, and go to 1 again, go to 2 again. So you will do this endlessly, right?
If
Yeah?
you are 2, why would you choose 1?
Because 1 is also connected to 2, right? It's a
So
bidirectional.
why don't you choose 3?
Yes, you can choose the 3 as well. I mean, expanding the nodes, right?
So
If
why-
I add 2, and what are the nodes it can lead to? Yeah, we look up these. List here is 1 and 3. Am I right? Look, Eric. Look here. Yeah, okay. So today we talk about depth search. How are we usually implementing the depth search? How are we usually implementing the depth search? What's depth search? Huh? What's depth search?
No, I mean tail. I mean
Pass exists from this.
stack.
Yeah, and then how are we usually implementing it? Using what? Start with R, or what do you call it? Edges. Okay, edges. Okay.
What begins with R?
What?
Reduce.
Calling itself.
Reorder.
Calling itself. What does it call?
Repetition.
Recursion, right?
Recursion.
Yeah, recursion.
I was
calling
about to
itself.
say.
Yeah,
Me
maybe.
too. But I
So
accidentally said
first of all,
repetition.
we given this list of edges we want to form. We want to build a graph, right? We build a graph with adjacent matrix. Okay. So okay, come on. G equals before what?
Before dictionary.
Before
just kidding.
yeah, before
Before
dictionary, and then list of int. Okay, which is because look, the keys are what are the keys, Eric? The graph. Remember we just talked about this 2 minutes ago. What are the keys in the graph?
Vertex.
Vertex.
Edges.
Okay. Now look for
Edges.
SE
Look.
star end in
Vertex.
edges.
Edges.
In edges.
Look.
And what should we do now? What should we do now?
G.
S
S.
dot what?
Dust.
GS dot what?
Pop.
GS dot what?
J. G. S. A pen.
A pen what?
E.
Okay, and then
G. Dot S.
why is that? Why is that?
Because we paper.
Why we do this? Can you tell me why? Why append E and G dot append S? Why? Why, Eric? Why? Look, this is S, this is E. Remember the bidirectional. If S can go to E, then E can go to S, right? Yeah?
Yeah.
The trees are directional graph. Why is that? Look, this is a tree. Why is that? It's actually, look, the trees we talk about, right? It's actually directional graph. Why is that? Because look, you cannot go to the parent. Usually you cannot go to the parent from the kids, right, Eric? So it's a directional from parent to the kids, right? Got it? Alright, this is tree. Directional, right? But now we are talking about bidirectional or unidirectional, yeah? Unidirectional. Unidirectional, okay? Alright, does it make sense?
Yeah.
Pay attention, okay? You're losing focus, okay? You're thinking about something else, right?
No, I'm not.
Okay, that's it. Geez, okay, and then now, first of all, we need to remember, have a set.
Scene equals set.
This is to remember the nodes, the vertex we have visited, right? Yeah, so we don't do this again, right? Yeah? And then what? Then we have these define, we have a define depth of
You
search.
forgot something.
What?
Cash.
We don't need cache at the moment, right? I told DFS,
Cash.
DFS what? Star, with the star to the end, right? So what does it mean? We want to find out if there is a path between S to E, right? And then what do we do? If S equals E, what should we return? This is the base cases.
True.
True, yeah? Because look, if star and
Scene
E,
dot
well,
add S. Scene dot add S.
why?
Yeah.
Return true, where? Yes, we're done. Because sin is the number of nodes we visited. We are currently at S, so we need to put it at here, yeah? Sin dot add S. This is a set, yeah? Add S. And then what should we do now? We should iterate over the nodes that the GS, right? Okay, so if I'm at S, what are the nodes what are the vertex that are the
GS.
Okay, can you listen to me, okay? We are at current node, the vertex S. What are the nodes? Where can we access the list of nodes that the S connects to? Remember, this is the S, and then it connects to a few nodes. So how can we access it? Where do we add it? Where are the values? Where is the graph?
GS.
Yeah, that's okay. So we go through the node, yeah.
That's a spirit.
For I in what? In what? For I in GS, right?
GS.com.
Okay.
GS.com.
Now what do we do now?
Beep beep.
If
Beep beep.
Ryan, don't play with the cat. Come on, listen. This is the coding lesson, okay? So I is the node that look Eric. This is I, yeah. So first of all, we need to check if we have seen this I before, right? Yeah. Look, so we do what? If what? I not in what? Eric. If I not in what?
If I not
In what? What?
Scene.
Yeah, well done. Because look, this is the hash set.
I just thought I heard
yeah.
a bird.
And what? And
Oh.
if we can do this, if we can visit it, if fs what? And return true. Can you tell me? Otherwise, return false here.
Avoid return false.
Can you tell me what should I put here? If I is not in scene and DFS, we are calling itself to find out what are the two parameters here.
SE.
S?
IE.
IE, well done. Why is it IE?
Because that's a mum.
What? Because look, the I is the S connects to look, right? Because listen, E is somewhere here, right? I don't know, right? But look, S the next node is I, right? I know S can go to I. And I want to find out if I can go to E, right? If I can go to E, then I know if S can go to E, am I right? Simple as that, right? So, but we have to check if I is not in the scene, right? We want to make sure we don't visit this I over and over again, right? So if I not in scene, and then we can, if we find out that I can be connected, there's a path between I and E. What does it mean? Alright.
That is true.
Yeah, look. I, what's I? S, there's a path between S to I, right? Alright? Alright? Because S is connected to I. And then there's a path between I to E. What does it mean? The connectivity. S can go to I can go to E. So what does it mean? Oh. S can go to I can go to E. What does it mean?
True.
What's true?
It's
S can go to E. There's a path. Look.
start.
Yeah. Look. Start and E. There's a path between S to E, right? Got it? Yeah? Does it make sense? Does it make sense, Eric? We just need to return S to E. Okay, so Ryan, you mentioned a good point about the cache, yeah? Which is good.
Ryan just looked at her.
That's fine. What's cache mean? What does the cache mean? Cache is what does this cache mean?
So it's not educational or whatever. Explanation. Blah blah blah.
What's cache mean? What does cache try to do here?
So memorization.
Yeah, memorize. What does it try to memorize?
So it doesn't go over again.
Yeah.
Yeah.
Okay.
Yeah.
No. People can't see that. Okay. So what?
And then
Eric.
this one.
Okay,
is
Eric,
else.
the cache, memorize. Okay, so if you are calling the S to E, right? And then if somehow later you want to find out again, we don't calculate this function. Because we already calculated.
Yeah.
We already calculated. Then that's why we just look it up in the notebook. Then we can directly return the value. Do you get it? Do you get it?
Yeah. Yeah.
Okay, so look, if we want to replace this cache, can you tell me what to do? If I don't want to use this trick, how can I memorize it?
We want to use it in the trick.
And how about if I tell you can't? So
We don't care. We just do it.
Yeah, you just do it. But how? If we want to memorize, we use what? What kind of
Dictionary.
thing? Dictionary, yeah.
But
So
we
we-
already got a dictionary.
So we just want to look. So how can we do this? We just put a dictionary like Mimo, yeah? Mimo equals default dictionary,
Mimo,
yeah?
it sounds
Default dictionary, we should return the value will be true or false, right? So it's a boolean, right? What's boolean, Eric?
A bully.
Boolean, what's boolean?
A bully is a mean person. Yeah.
Boolean. No, boolean. What's boolean? What does it mean?
Is a bully.
Boolean, true or false? True or false? Boolean.
False.
True or false. It means true or false. Yeah? It's a value of true or false. Look, so with default dictionary, the default type is a boolean. Yeah, Mimo. And then here, what do we do? If, we just put here, if look at tuple, yeah? SE in Mimo, then what do we do? Return Mimo, yeah?
Got it.
Mimo SE, Eric, look. And then before returning, Eric,
It is a rubber.
Eric, Ryan, before returning true, we said Mimo, this is a tuple, yeah? SE equals true, right? And here, what do we do here? Before returning false, what do we do? Mimo
My bases.
SE equals what? Mimo SE equals what?
False.
False, yes, we're done. Look, so basically, right before we returning true or false,
Yeah.
we set the key, Eric, look. We set the key of the dictionary, Mimo, right? Which is, look, what parameters are here? What parameters are here?
Anthony.
S and E, right? So we set the S and E, tell tuple to true or false. So basically we remember the values, yeah? Got it? We remember the values. So you speed up if you have these multiple calls to the same input, S and E, right? Got it? Okay, let's do this. That's it.
Oh my god.
Come on.
That's
What are we doing here?
impossible.
You understand what do you mean you don't?
If I know.
Okay.
If I not in C and DFSIE,
return true. Yeah, you always memorize the easiest part. Okay, so in what cases are we returning true? Come on, try to understand. Try to understand the problem. Okay.
If I not
What's I not
in scene and DFS, i.e.
Do you need and tell me why? Okay, because you're looking at the answer.
So.
If I not in C and what? And what? And we accordingly say, yeah, and DFS what? I just told you DFS what? From what? I to the, what's the destination? E, yes. And like returning to, yes. Column. What's the time complexity? What's the time complexity?
N.
Yeah, n is the number of nodes in the vertex in the graph. What's the space complexity?
Among Us.
It's the same, yeah? Alright?
Among Us.
Okay, that's it for today.
Bye.
Bye bye.